Hello all, I'm Ishaan Mehta and today I'll be presenting on our work of gradient based auto exposure control applied to a self-driving car. Cameras are used in self-driving cars for various tasks like object detection, visual odometry, SLAM, etc. Hence, well exposed images are an essential prerequisite for these operations. However, this is typically not achieved due to limitations of the camera sensors. So in this work, we present an exposure compensation method for self-driving cars. We implement this algorithm on AU Toronto's self-driving car ZS as shown in the figure. Most camera sensors have a small dynamic range which limits their ability to capture illumination levels of a natural scene. This results in under and overexposed regions of images. The built-in auto exposure algorithms of the camera in a lot of cases are unable to generate useful images for our applications, as it can be seen in these images on the slide. So the algorithm we use attempts to reach exposure and gain settings that maximizes the image gradient. This is done by taking the current image from the camera and applying 7 gamma corrections and computing gradient information for each gamma correction. A fifth order curve fitting is done over the pair of gammas and gradient information. This curve is used to search for optimal gamma that maximizes the gradient information. Finally, current exposure, gain values, and optimal gamma are used by camera update function to update the camera with new shutter speeds and gain values. In this algorithm, we use gradient information. The gradient information of an image is sum of the gradient metric at each pixel. Gradient metric at each pixel is calculated using the gradient magnitude of the pixel using the formulas shown in the slide. Now coming to exposure update function, the input to the exposure update function is optimum gamma, current shutter speed and gain. In the first step, the current exposure values are calculated. Then the update to the exposure values is calculated. Note that here Kp, alpha and d are the tuning parameters. Based on the updated exposure values, new shutter speed for the camera is calculated. Now there are situations where the calculated shutter speed is beyond the allowable limits. In such cases, gain compensation becomes necessary. So the appropriate gain is calculated for the exceeding part of the shutter speed. Note that when we begin, we keep the gain values to 0. The output of the exposure update function is new shutter speed and gain values. So the camera is then updated with these new values. In order to validate the performance of the algorithm, we developed a ROS node to interface with the vision system of ZS. Our node acts as a supervisor to the camera driver, which provides external control and avoids superimposing additional computational constraints to the image acquisition process. Two identical cameras were mounted on the car in a parallel configuration to record videos in an outdoor driving scene as demonstrated in the image. One of the cameras used our node and the other camera used default auto exposure. The image streams from two cameras are compared based on number of features detected and gradient information in each frame. The plot shows frame by frame comparison of gradient information. It can be seen that images captured by our node consistently had more gradient information than the ones captured by the camera's built-in function. It can be seen in the video that visibility of useful features like traffic signs is much better for our node. Since our node was able to capture more gradient information, this should result in a larger number of features detected by image feature detectors. This is verified by the plot shown in the slide, which shows a frame by frame comparison of fast feature detections. Besides greater number of feature detections, our node captures more useful features for robotic applications. It can be seen in the image that image captured by a node preserves useful features, whereas in the built-in case, the features are concentrated in the sky region. So to conclude, in this work we have implemented a gradient-based auto exposure control algorithm on the vision system of a self-driving car. We have extended the algorithm to include gain compensation. The images from our system are rich in gradient information and as a result have higher number of feature detections. Thank you.